blow up beautifully. But this is calculate the wavelength of light emitted by each of the following transitions that occur in the hydrogen atom. What type of electromagnetic radiation is emitted in each transition? Okay, well, the first thing is this. I could ask you a question like this, but I won't ask you the type of electromagnetic radiation because you'd have to know where the different frequencies or different wavelengths are, okay? So I won't do that, but we'll look it up anyhow. And I'm just going to do letter A for now. So A says calculate the wavelength. So I want lambda. And what else do they tell me? They tell me nothing else in this problem. They just say, what is the wavelength emitted? And then they give me this transition. So this electron's dropping from 4 to 3, so it can emit light. So N initial is going to be 4, N final is going to be 3. So what we're going to do is solve this equation here, because that has N initial and N final in it. And that'll give us energy, and then we can get wavelength from using this. So these two equations can be tied together. A bunch of these equations can be tied together. So this is going to be delta E is equal to negative 2.178 times 10 to the negative 18 joules times 1 over N squared final minus 1 over N squared initial. And that's probably overkill writing it out again because I just wrote it, but I want to give it to you. You got it. Getting it down? You getting it down?
Yeah, I have the equation.
Let's check it. Let's keep my eye. All right, so delta E equals negative 2.178 times 10 to the negative 18 joules over 1 over final is 3 squared minus 1 over initial 4 squared. Delta E equals negative 2.178 times 10 to the negative 18 joules. Oh, by the way, too, I have a correction to a problem that I did yesterday with you guys. Remind me after this problem so I don't forget. I figured an easy way to fix it. So, what I gave you is not wrong, but it didn't answer the question that was in the book. Now, again, I'll go a little overkill here. This is 1 over 16, thank you. Or that's 1 over 9. That's 1 divided by 16. I don't know why that turned off, but it did. That's funny, that shifted too, didn't it?
Oh, yeah, I got mine.
Yeah, he had a different one. All right, thank you. Funny enough, Jarrett, when I did, I got this buried. I don't know how that got buried down there. I think you guys were probably out that day with class. Okay. So again, don't waste your time trying to get common denominators and stuff. Just divide those things out. So delta E equals negative 2.178 times 10 to the negative 18th joules times 0. Pretty sure that's 0.111. 1 divided by 9. 0.111, yeah. And then 1 divided by 16, that's 0.0625. So I'm going to put one more 1 in there to match up with that 0.0625. Okay? Delta E, negative 2.178 times 10 to the negative 18 joules times 0.0 minus 0.0486. Now, obviously, I'm putting a lot more steps in this than you probably would need to do. You probably don't have to write that first equation out, and if you just plug those in, I'd probably go straight from this to this, right? I'm just showing you that so you see each individual step when you go back and study. I'm not saying you have to go through that rigorously. Okay, so now I can multiply this out. Negative 2.178 times 10 to the negative 18 times 0.0486. And I get a negative sign because light's being emitted. Negative 1.06 times 10 to the negative 19th. Negative 19th would be joules. Okay, so now I calculated delta E. Now we got to go back and get what the wavelength is. So E of a photon. And I want the one with wavelength, so it's going to be the one that's NHC over lambda. What's that?
What did you say again?
I said, I got delta E, so I know how much energy is going to be involved in that transfer from n equals 4 to 3. That's how much energy. Now to get the wavelength, because that's what they're asking for, I can use this equation because this relates energy to wavelength. So I don't want to use the NH nu form, that's frequency. I want to use the NHC over lambda because that's what I'm looking for. So I can rearrange this again to lambda equals NHC over E of the photon. So I just rearranged it. So lambda equals, what's n going to be in this problem?
Number of photons.
Which is 1. It's one quantum drop, one electron drop. H is 6.626 times 10 to the negative 34th joule seconds. C is 3.0 times 10 to the 8th meters per second. All divided by the energy of the photon. Now watch your signs. We want to ignore a negative sign here. I don't want my wavelength coming out negative. Wavelength's got to be positive. That's just direction. It's exothermic. So I'm just going to type in here 1.06 times 10 to the negative 19th joules. And if you track units, you can get meters out of there, but if you can't track units, as long as you put in good units, it's going to come out meters. So 6.626 EE negative 34th times 3 EE 8th divided by 1.06 EE negative 19th. And I get 1.88 times 10 to the negative 6th. 1.88 times 10 to the negative 6 meters. Okay, so that's slightly longer than visible light. Visible light's to the negative 7. If I go back and look here, I'm guessing this is infrared. So I'm just going back, and again, I'm not going to ask you this on the test. On page 276, they show you a spectrum, and they show you numbers, and so the negative 6 power. Yeah, that's down in the infrared. So you're just below visible light. That's probably heat. Yep.
What would this problem have to say if we wanted to change n to like 2 to 3 or a different number?
Yeah. Wait, I'm not following you.
Like when n, what would the problem say?
Oh, okay, yeah. Let's say, I'd say, how can I do this? Let's say, well, let's say I don't ask you to calculate an electron drop. Actually, how about this? How about, I'm just trying to think of ways I can word it. I'm trying to see if I got one that I assigned you already that's like that. No. So let's say in this problem, okay, let's say I said you have a particular frequency of light, okay, emitted by a mole of electrons. Okay, what's the energy of a particular photon? Well, then you'd have that there. That makes sense.
Yeah, so you're asking for more.
Yeah.
That's so you can't.
Yeah, sure.
So you either only ask for more or like 1.
Usually, yeah. I mean, I'm not going to ask for like 13. You know what I mean? It's kind of weird, yeah. Yep. Jake?
For the energy equation,
Yes.
would it always be 1
For which over here?
No,
I did.
Oh, the ones up here? We're always going to be using hydrogen, yeah. We're going to just assume that.
So what about the number of particles?
Yeah, 1.
Yeah.
That's what he was just asking about. So if it's just one electron dropping, then it's just going to be 1 photon of light. If it was a mole of electrons, then you'd use 6.02. Is everybody good on this one? Okay, can I make a correction? Can you go back to your problems from yesterday that I gave you solutions to? And I gave you a problem solution yesterday for 42A. Is everybody? What's that? 41A, sorry. Oh, okay. Oh, okay, yeah, there was a problem with it. Okay, so 41A. I think what I gave you wrong was, no, I didn't. We did it right. Okay, did we use 9.11 times 10 to the negative 31st?
Yeah, that's right.
Do we use 3.0 times 10 to the 7th?
10 to the 8. 3.0
Times 0.1?
Yeah, we did.
Okay, good. Then it wasn't a mistake. For some reason, I thought I made a mistake there. No, we didn't. Okay, let's see. Let's go to now number 51. Okay, I think this one's worth showing. Oops. Okay, now this is a very similar problem, but I just want to show you something different here. This is calculate the maximum wavelength capable of removing an electron in a hydrogen atom for the energy state characterized by n equals 1 and n equals 2. Well, let's do the n equals 2 one just because n equals 1 is kind of boring. So here's the trick, all right? This is going to be, again, a delta E equals negative 2.178 times 10 to the negative 18 joules times 1 over n squared final minus 1 over n squared initial. All right, so delta E equals negative 2.178 times 10 to the negative 18 joules times. Okay. So the electron's starting out at n equals 2, or n equals 1 in this problem. So the initial is going to be 1 over 2 squared. What's going to be the final energy state? You're removing the electron. No,
Negative 1?
no,
0.
no,
1.
no.
Ground.
6.
So if I hit it with energy, it's going to get boosted to a higher energy level, right?
Yeah.
I want to know how much energy it's going to take to remove the electron. So it's not going to go to 1, it's not going to go 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11.
100.
It's not going to go to 100. It's going to go to infinity.
What?
Okay? So this is going to be 1 over infinity squared, which is kind of silly to say infinity squared, but you can. There's different kinds of infinities, right, if you watch like Mathologer and all that. Okay. What is 1 over infinity?
0.
It's 0.
Yeah.
Really?
Yep. Think about it. How many times does infinity go to 1? It doesn't.
Keeps going.
It's not even 1. No, infinity go into 1. Infinity divided into 1. 1 divided into infinity goes forever. But infinity never divides into 1. It's way too big.
That's not.
If you have a box,
Think about it this way. Just think about it this way. Okay, it approaches infinity. Let's put it that way. It's asymptotic. Think about it like this. 1 divided by 1 is 1, right? 1 divided by 2 is a half. Cut in half, got smaller. 1 divided by 3 is a third. 1 divided by 4 is a quarter. The number just keeps getting smaller as I increase the denominator. So if I take the denominator to infinity, that goes to 0. Keeps getting smaller and smaller. Make sense?
yeah.
So this is going to be
If
delta
you
E.
have a box that holds 1 M&M, how many times
So-
can you put infinity M&Ms
If
in
infinity
that
never stops, does that mean it's
box?
like is it even a value? If it never stops?
It's an incredibly large number.
Why is
And
it
that's what
not-
I'm saying, is that it
why is
doesn't
it
matter
not
how far we
undefined?
go, that number just keeps getting smaller.
Why is it not undefined?
It's because it's 0. It is 0. Like, it can be shown mathematically. I don't know how to do that. I'd ask the math teacher. But just think about it the way I'm saying that logic. Follow the logic I'm saying. If you keep making that denominator bigger and bigger and bigger, it keeps getting closer and closer to 0. And if you imagine an impossibly big number, it's going to get impossibly close to 0. That'd be my argument. So this is 0 minus negative 0. Minus 0.25. We okay here? Okay, so really it's just coming out positive now. 178. Wait, everybody getting all riled up back there.
Since there are an infinite amount of energy levels, you need
Is this all the infinity thing? Or is just everybody talking?
Wait.
Since they're
If I get
infinitely
any squared on the
outnumbered,
keys, I think I'm just gonna walk up and turn in, because I'm probably doing something wrong.
Infinity squared? No, that's 0. I'm telling you, that's why I'm teaching it to you.
I know, but
Because it says you wanted to get rid of the,
Okay, so again, we can just go to this now.
if it doesn't give you a final.
Okay, so lambda equals NHC over E of photons. So this is the same thing again. Lambda equals 1, 6.626 times 10 to the negative 34th joule seconds times C 3.0 times 10 to the 8th meters per second divided by 5.44 times 10 to the, oh, this is, sorry. Guys, hey, we gotta settle down. Negative 19th, I had positive there, so make sure if you copy that, that's the same. And notice too, that came out positive this time. And it came out positive because the light is going in and striking the electron and boosting it, as opposed to it dropping and giving off light. So 6.626 EE, negative 34th, times 3 EE 8th, divided by 5.44 EE negative 19. And I get 3.65 times 10 to the negative 7. And that's just outside the range we can see. We can see 300 nanometers to, or 400 nanometers to 700 nanometers. That's just below 400 nanometers. So that's just into the ultraviolet bit. Okay. Yep.
the problem did yesterday, why did you times the 3.0 times 10 to the 8 by 10?
Because it was 10% the speed of light, and that was in this equation here. Yep. Because so that would have been velocity. Yep.
What is the 2 in the back end?
The problem.
Yeah.
The problem's saying you got.
6.626.
Hey guys, can we settle down? I mean, if I can answer a question, I gotta be able to hear. Originally, it wants to know how much energy do you have to remove it if it's at 1. So that means that how much energy do I have to go boom to shoot that thing off to infinity? In the second case, we're now at n equals 2. So this is n equals 1. Now we're at n equals 2. Say, now what wavelength would it take to boost that off to infinity?
So all you do is change where we have 1 in the problem?
Exactly.
Okay.
So really what it would be is this would be 1, this is why I didn't do it because it's boring. It'd be 0 minus 1. It would just be that number right there positive. Because this would all go to 1, or negative 1, and times the negative it would go. Okay? Yep.
What was something with infinity squared?
You could. Yeah, it could. Now, what else can come up, and it's in some of these problems here too, is I do expect at this point that you guys can do basic algebra. Okay? All right? That's an expectation that I have. All right? So, let's say I gave you delta E, and I gave you initial or final state. You should be able to solve for one of these.
Nudge.
I'm just saying. You
Is
should be
that
able to.
like the photoelectric effect, where it shoots off an electron?
Can you do one where
Yeah.
you solve for that?
Yeah, well, you got one in the homework, so I'd say give it a shot. If you have a question, shoot up on a note or ask me or something like that. I want to go back and make sure we get through some of the other types too. We good here? Yes. This was no, this was 51.
No, the one where we have to find, where you give us negative 44 minus the.
Oh, okay. 48. Did I give you 48 yesterday? Did I? Because if I did, that's okay. Yeah, I did. Okay. So 48, basically all they're saying is this. For 46, they want to know. Okay, I'm sorry.
Sorry, I didn't see it on the bottom.
46, we just looked at the one that says n equals 4 to n equals 3, right? And what they want you to do, and they show this in the book, if n equals 4 and n equals 3, this is n equals 1, n equals 2, n equals 3, n equals 4. We have an electron that's going from here to here. That's basically what they wanted to show. And I probably won't ask you to do that on a test. It's more just to get you to visualize what's going on.
That's a good question.
Can Infinity come up with another type of problem?
In these, I don't think so. No, that's the only place I see infinity coming up.